Welcome back to the deep dive. Today, we're opening up the blueprint for something called DeepAgent. It's an end-to-end deep reasoning agent.
Right, and it's really designed to tackle what's maybe one of the biggest headaches right now with large language model agents.
Yes.
Getting them to reliably use real-world tools, especially when tasks get complex and stretch out over a long time. Long horizon interactions.
Okay, so that integration challenge.
And what's interesting is how DeepAgent kind of frames the problem.
Mm-hmm.
These traditional agents, they often get stuck in these really rigid, predefined loops.
You mean like that reason, act, observe cycle we hear about?
Yeah, that sort of thing. And it works okay for simple steps, but it really breaks down when things get messy. Like when the agent needs to dynamically find the right tool from maybe thousands, or when the conversation history just gets enormous.
A context window explosion problem.
That's it. These fixed workflows, they just don't give the agent the autonomy or the kind of big picture view it needs for really complex stuff.
So, our mission today is to unpack how DeepAgent tries to solve this. We're going to look at, well, three main ideas, right?
That's right. There's its core architecture, this unified agentic reasoning idea. Then there's its clever memory management, this autonomous memory folding.
Sounds intriguing. Brain-inspired, I think.
It is, yeah.
Yeah.
And third, the specialized way they train it using reinforcement learning, something called ToolPO. The big idea is really unifying the thinking, the tool finding, and the doing into one smooth, adaptive flow.
Okay, let's start with that unified reasoning process. You said it ditches the fixed cycle. How does that actually work in practice?
Well, instead of that step-by-step reason, then act, then observe, DeepAgent is kind of always thinking, searching, and acting as needed within one continuous stream.
So it's not stopping itself constantly to check boxes. It just decides, okay, now I need to think a bit more, or now I need a tool, or now I need to execute this.
Pretty much. It bases the next step on the overall state of the task where it's trying to get to.
And that continuity, that helps it keep the big picture in mind.
It does. And critically, it totally changes the game for tool use. Instead of grabbing a whole bunch of tool documents, upfront stuff it might not even need, and stuffing them into the context.
Which eats up tokens fast.
Right. Instead, it discovers tools dynamically, only when it figures out, I think I need a tool for this part.
Okay, how does it signal that? Does it just type, I need a tool?
Huh? Not quite. It generates a specific signal, a special textual prompt. It looks like tool search, then the actual query, QS, and then tool search.
Ah, structured. So the system knows exactly what's being asked.
That query then goes into a dense retrieval system, searches against embeddings of all the tool documentation, finds the best matches, and sends the info right back into the agent's reasoning stream.
So it gets the documentation just when it needs it.
Okay.
And then to use a tool, another structured call.
Yep. You use a tool call, and inside that, it specifies the tool name and the arguments in a structured format, like JSON.
That makes sense for reliability. But wait, if you're searching huge API catalogs, like Rapid API or something, the documentation could be pages long. And the output from the tool could also be super verbose. Doesn't that just bring back the context length problem?
Good point. That's where another piece comes in, an auxiliary LLM. Think of it like a helper, or maybe an editor.
Okay. What does the helper LLM do?
Its job is basically to shield the main reasoning agent. When lengthy tool documentation comes back from the search, this auxiliary model steps in and summarizes it before it hits the main agent's context.
Oh, interesting. So it pre-processes the info.
Right, and it does the same for verbose tool outputs. It condenses them down. So the main agent only sees the useful, concise information it needs to make the next decision.
So the auxiliary model's role is purely context management, keeping the main agent focused. That seems vital, especially for longer tasks, which brings us neatly to the next big challenge DeepAgent addresses, that context length explosion on long horizon tasks.
It does. And this is where the autonomous memory folding comes in. It's a really neat idea, quite brain-inspired, as you said. Think about trying to follow a super long email thread or meeting transcript.
Yeah, you lose track completely.
Right. So DeepAgent can basically decide for itself, okay, this history is getting too long, I need to compress it.
It tells itself to sort of summarize the last chapter.
Exactly. It does this by generating another special token, fold thought. It can trigger this whenever it makes sense logically. Maybe after finishing a subtask, or even if it realizes it went down the wrong path and needs to back up and rethink.
And when it generates that fold thought token,
the folding mechanism kicks in. It processes the preceding interaction history, all the thoughts, tool calls, observations, and replaces it with a structured, compressed summary.
that must save a ton of tokens and keep things efficient. But summarizing its own history, isn't there a risk? What if the summary is bad? Then the agent's planning is based on faulty information.
That's a key concern. And it's why the memory isn't just a single block of text. They designed a brain-inspired memory architecture. It uses another auxiliary LLM, actually, to generate 3 distinct memory components in parallel.
3 components. Okay.
Yeah, and it uses a structured JSON schema to make sure they're reliable and useful.
So what are these 3 parts? What do they do?
Okay, first, there's episodic memory, which they call MEUSDR. This is like the agent's long-term diary. It logs high-level progress, key decisions, the main goals. It provides that long-term context.
Got it. The big picture log. What's next?
Second is working memory, or $. It's more like short-term memory, the agent's mental scratch pad. It focuses on the immediate task, the current sub-goal, any problems it just ran into, the plan for the very next steps. Keeps things flowing smoothly from moment to moment.
Okay. Long-term and short-term. And the third must be about the tools.
You got it. Tool memory, MDS. This specifically tracks the agent's experiences with tools. Which ones did it use? How did it call them? And importantly, did they actually work? Were they effective?
Ah, so it learns about its tools over time.
By structuring memory this way, episodic, working, and tool-specific, they get the benefits of compression during folding, but they minimize the risk of losing critical details.
Okay, so we have this unified, continuous reasoning, dynamic tool use, and this clever, structured memory folding. But even with a great architecture, the agent needs solid training, especially for using potentially thousands of tools. Which brings us to ToolPO.
Right, the reinforcement learning part. And training agents with RL, especially for complex tool use, usually hits 2 big snags you mentioned earlier: cost and stability, and also sparse rewards.
Let's talk about sparse rewards first. Why is that such a killer for these long, complex tasks?
Well, sparse rewards means the agent might go through dozens, maybe hundreds of steps, thinking, searching, using tools, and only gets feedback, like success or failure, right at the very end.
So it doesn't know which step was wrong if it fails.
Exactly. It's like, imagine trying to learn baking, but you only find out if the cake is good or bad after you take the final bite. You have no idea if you messed up the mixing, the temperature, the ingredients somewhere way back at step 5. It makes learning incredibly inefficient.
Okay, so ToolPO needs to fix that. But before we get to how it provides better feedback, how does it deal with the first problem, the cost and instability of training on potentially thousands of real-world APIs? Calling real APIs constantly during training sounds expensive and, well, flaky.
It would be. So they built something really smart, an LLM-based tool simulator.
The simulator.
Yeah. They train another LLM to basically pretend to be thousands of different real-world APIs, like the ones you'd find on Rapid API. It learns to mimic their responses.
So the agent interacts with the simulator during training, not the real, potentially slow or unreliable APIs.
That's the idea. It creates a stable, fast, and much cheaper environment to do all the trial and error learning needed for RL without constantly hitting external services.
Okay, that handles the stability and cost. Now back to the sparse rewards. How does ToolPO give the agent that crucial intermediate feedback, that fine-grained learning signal?
It uses 2 types of rewards. There's WATSOK, which is the overall task success reward at the end. But crucially, there's also reaction.
An action-level reward.
Right. This reward evaluates the quality of intermediate actions, like whether a tool call was made correctly or if memory folding was used efficiently at a good point.
So it gets little bits of feedback along the way.
Kind of, but the really clever part is what they call tool call advantage attribution.
Advantage attribution, what does that mean?
Okay, in RL, advantage is basically a measure of how much better a particular action was compared to the average action in that situation. Instead of smearing this advantage calculation across all the words the agent generated in a step.
Which could be a lot of words, thinking out loud or processing tool output.
Right. Instead, ToolPO attributes the action level advantage, Azure level day, only to these specific critical tokens that actually make up the tool call instruction, like tool call, or the memory told instruction, full thought.
Oh, I see. So the credit or blame goes directly to the decision point, the exact moment the agent decided to call a tool or fold its memory.
Precisely. It provides a really focused local learning signal. It teaches the agent when to make those critical moves, not just rewarding or punishing the entire chunk of text generated around that move.
That sounds much more effective for learning specific skills like tool use.
Okay, so this all sounds good architecturally, but does it actually work? What did the experiments show? They tested it on quite a few benchmarks, right?
They did, across 8 different benchmarks covering general tool use, things like ToolBench, interacting with Spotify, ToolHop, and also downstream applications like ALFWorld simulations, WebShop e-commerce tasks, the really tough GAIA question answering, and even managing home environments.
And how did DeepAgent stack up? The results were pretty strong, especially for the RL-trained version. Let's look at the 32 billion parameter models for comparison. On general tool use, like the TMDB benchmark where the tools are known but complex,
Okay.
DeepAgent 32BRL hit an 89.0% success rate. The best baseline they compared against, Kodak, was way back at 55.0%.
Wow, that's a huge jump, nearly 35 points. That really suggests the unified reasoning beats the old workflows.
It seems to. And then in scenarios where the agent had to find the right tool first, the open set retrieval cases like ToolBench DeepAgent 32BRL still came out significantly ahead, getting 64.0% success compared to the best workflow baseline at 54.0%.
So it's good at both using known tools complexly and finding the right unknown tool. What about those long horizon tasks where memory should matter most?
That's where you really see the architecture shine. On GAIA, which is known for being very complex, multi-step, needing web interaction, DeepAgent 32BRL scored 53.3.
And the next best agent?
That was higher at 42.5. So again, a pretty substantial lead for DeepAgent on these really long, tough problems.
That strongly points towards the memory folding doing its job. Did they do ablation studies, like turning off parts of DeepAgent to see what happens?
It did, and it confirmed exactly that. When they removed the autonomous memory folding mechanism, performance dropped significantly.
Especially on the long tasks, I bet.
Yep. On GIA, the score fell from 53.3 all the way down to 44.7 just by taking out memory folding. It really needs that ability to compress and refocus its history for long-term planning.
Okay, that makes sense.
And one other thing the experiments showed was about tool discovery. DeepAgent really worked best when it used dynamic tool discovery, finding tools on the fly. Its average success across those open set tasks was 52.6.
Compared to?
Compared to only 42.0 when they tried pre-retrieving all the potentially relevant tools up front. So the agent really benefits from deciding when to look for a tool, rather than being given everything at the start. The architecture seems built for that dynamic interaction.
So wrapping up the main takeaway here, DeepAgent offers this unified way for these big reasoning models to handle thinking, finding tools, and using them all in one go. And that seems key for tackling complex, real-world stuff that needs lots of different tools.
That's the core message. It's a framework designed for autonomy and scalability in tool use. But there's maybe one final, quite provocative finding from their scalability tests.
Oh, what's that?
They tested DeepAgent not just with 30 billion parameter models, but scaled the backbone LLM all the way up to a massive 235 billion parameter mixture of experts model.
Okay, a huge model. Did performance just skyrocket equally for all methods?
Not exactly.
Right.
Even with that enormous base model, DeepAgent still maintained a significant performance edge over the older workflow methods like React or Plan and Solve.
So just making the underlying LLM bigger wasn't enough to close the gap.
It seems not. It suggests that the architectural choices, the unified reasoning, the dynamic tool discovery, the memory folding are actually fundamental to unlocking the capabilities of these large models for complex agent tasks. It's not just about throwing more parameters at the problem. How the agent is structured matters, maybe even more so at scale.
Interesting. So the way the agent thinks and manages information is potentially more critical than just raw model size, especially for these really advanced applications. Something definitely to think about.